Hi guys. So this is the final lecture in this introductory course in corporate finance, and I want to conclude this course on an important topic called the Modigliani-Miller Theorem. So in this theorem, we basically want to show that under strong, specifically the same assumptions we already made under the CAPM model, we can actually conclude that a firm's capital structure is irrelevant to a firm's fundamental value. And so why is this important? This is important because we kind of neglected we kind of ignored the topic of whether or not there is some sort of optimal capital structure in which a firm can take on to essentially maximize the firm value. So what that means is that what does it matter whether a firm decides to finance itself completely with equity, or is there a different valuation if a firm decides to finance its operations through debt? According to this theorem, it doesn't really matter. And in fact, when we do our valuation homeworks in this class so far, we kind of assume that it must be true. And so what I want to do here in this lecture is kind of go over the assumptions necessary in order for us to conclude that actually capital structure doesn't matter. Okay, so the Modigliani-Miller theorem actually has three parts to it. So let's just go over the first part first, which is the key finding that a firm's total market value is independent of its capital structure. Okay, so again, capital structure just means the way in which the firm's operations is financed. And we typically represent a firm's capital structure with a ratio, namely the debt to equity ratio. So I'm going to write D over E to represent debt over equity, but sometimes we also talk about D over V to represent our leverage ratio, which is also another way to measure how levered a firm is, or represent a firm's capital structure. Okay, so proposition 1, the assumptions that go into this claim are actually the same as CAPM. So in terms of, as you know, CAPM has three fundamental assumptions. We don't need the mean variance portfolio assumption in which investors optimize a mean variance portfolio. That's fine, but we still need the assumptions in which markets are essentially frictionless and competitive. So that means no transaction costs. Individuals and firms are price takers, meaning that there is lots of buyers and lots of sellers willing to buy or sell any asset in the universe. And lastly, we also have to assume that there is perfect information. That just means that information sets across all investors are the same. Okay. In the first proposition itself, Modigliani-Miller actually proved it under the case in which there are no taxes or no tax cuts. Tax rebates. But we don't have to keep that assumption. Actually, we can actually relax it later on, but for the sake of simplicity, we will first keep that there so that the mathematics is simple. Lastly, we also inherently have to assume that a firm's cash flows do not depend on its financing policy. So what that means is that each firm's periodic cash flow is not a function of debt over equity. Okay, so that's not true. We assume that cash flow each period is independent. So I'm going to use this upside down T to represent independent from D over E. Okay, so under what cases would cash flow be dependent on our capital structure? So you can imagine the scenario in which there is bankruptcy costs. So if you believe that if a firm decides to file for bankruptcy, it may have to incur restructuring costs, for example, of hiring lawyers and experts to redesign and restructure a firm's leadership and management organization. Okay, so that's just an example. And there are ways to model that directly into the cash flow. But for Modigliani-Miller's theorem, first proposition, we're going to assume that cash flow and leverage ratios are not dependent on one another. Okay, so we're going to prove this proposition first. In fact, we're going to prove it using the simplest way possible, using the same math that we've seen before. So rather than prove it under what was presented in their paper in 1958, we're going to prove it using CAPM. Okay, so in 1958, they actually proved it using a no arbitrage argument. We're just going to prove it using the CAPM assumptions. So given the CAPM assumptions, we already know that we can have the CAPM formula. So CAPM is defined in the second bullet point, and it states that a firm's or an asset's returns is equal to the risk-free asset plus its exposure to the market risk premium. So that's the exposure to the market risk premium is represented using beta, so beta E. So in order to extend this model so that we can incorporate capital structure in it, we want to first assume that debt beta is going to be 0. So we're going to assume that there is no default risk if a firm, so that means that if a firm decides to issue debt, its cash flow is deterministic. There's no risk whatsoever in its cash flow, and it will pay out until the end of its maturity. Okay, so given that assumption, we can then use the unlevered beta assumption to reformulate an expression that incorporates the D over E ratio. Okay, so let's start out with the beta U, or the unlevered beta expression, which is a weighted average between the debt beta. So I'm going to write D over V for the proportion of a firm that's financed by debt times beta D, plus E over V, so the proportion of a firm's value that's financed by equity times beta E. Okay, and also we assume that beta D is 0. We can therefore rewrite at the asset beta, or the unlevered beta, equal to E over V times beta E. Okay, reorganizing that expression and realizing that the value of the firm is equal to D plus E, we can arrive at this following expression. Beta E equals to 1 plus D over E plus beta U. So using this expression, we can substitute that directly into beta E in our CAPM equation and get this following expression here. Okay, so now we have our CAPM formula, and we also have our debt to equity ratio in the expression as well. So we have a relationship between the cost of capital of equity and D over E. So the final total cost of raising capital, D plus E, therefore can be written as the return on the amount that you have to pay back times the amount of debt or equity you borrow. And so we take D times R to represent the amount of money you have to pay if you decide to take on a level of D debt, plus the amount of equity times RE, which is the amount you have to pay to equity stakeholders and its return. Okay, so writing this expression using the adjusted CAPM formula, we can arrive at this following expression, and rearranging the terms, we come to this final expression. So it may not look like we arrived at any sort of enlightening conclusion here, but what you should notice is that the ratio of debt to equity is no longer in our formula. So actually what this tells us is that the cost of raising capital, D plus E, is irrelevant to the debt to equity ratio, right? It's not in the equation, so therefore they don't determine one another, and it doesn't determine each other, vice versa, okay? So that is the final conclusion of, or the main conclusion of the Modigliani-Miller theorem in its first proposition. Namely, the cost of capital is irrelevant to how a firm is financed, whether it's through debt or through equity, or it's anything anywhere in between. It doesn't matter. The firm value is the same. Okay. All right. So it may not seem like it's important so far, but just note that this is the fundamental assumption that we're actually using when we value firms. Okay. And in fact, we can extend this proposition to include tax shields, and the conclusions for proposition 1 still follows through. Okay. All right. For the second proposition in Modigliani-Miller 1958, they claim that a firm's cost of equity is equal to its debt a firm's cost of equity increases with respect to its debt to equity ratio. So they want to basically show that if a firm decides to increase debt relative to equity, that will lead to an increase in the equity cost of capital. That's what they want to show. So this has nothing to do with default risk or the consequences or cost that arises when a firm decides to file for bankruptcy, or the cost of not being able to recover the principal amount of money that debt holders decide to invest in the firm. This is just a mechanical relationship between debt and equity and the cost of capital of equity that arises from Proposition 1, but it's unrelated to the bankruptcy costs. Okay, so that's something completely different, and in fact that's captured by the debt beta, or you can actually formulate it directly into the cash flow statement formula as well. But in any case, this is just showing that equity beta, the cost of capital of equity mechanically increases when a firm decides to leverage up, and it has nothing to do with bankruptcy costs. All right, so how do you prove it? The proof is actually even simpler than the previous proposition. So we simply start with the WACC formula. So this is the pre-tax WACC. We don't have tax shields yet. So as you know, the WACC is simply a weighted average between the cost of debt and also the cost of equity. So R here can be RF if it's risk-free, but I'm just using R to represent any debt return. Okay, it could be risky debt. And so again, we're weighting based on the proportion amount of the firm value in which it's financed by the respective security. Okay, whether it's debt or equity. Taking this WACC formula, we can then rearrange the terms such that RE, or the cost of equity, is on the left-hand side. And this allows us to pinpoint or kind of construct it in such a way such that there is a relationship between, again, debt and equity ratio to the cost of capital of equity. Okay, so by Proposition 1, we already know that how the firm is financed, or essentially, how the cost of the firm to finance its operations, or the WACC, is independent or unrelated or not a function of the debt to equity ratio. Okay, so that means that if one were to increase D over E, it will not have an impact on the WACC. Okay, that's what Proposition 1 essentially states. Okay, so once we have Proposition 1, then we know that all else equal, if we increase the debt to equity ratio, that will naturally, mechanically increase the cost of equity, RE, right? If WACC is unrelated to D over E, increasing D over E will cause RE to increase. Okay. So this, again, is just simply demonstrating that we don't need assumptions about bankruptcy costs to get this positive relationship between leverage and cost of capital of equity. This simply arises because of the first proposition that there is essentially a capital structure irrelevance to firm value. Okay. In most typical cases, I want to remind you that yes, WACC typically is greater than R. This is because WACC is a function of the cost of equity, RE, but essentially there should be no relationship between RE and R. Okay, there is no predetermined relationship between these two variables. But in any case, the conclusion of Proposition 2 tells us that if we increase the debt to equity ratio, it will mechanically increase the cost of equity. Okay, and this is solely based on the CAPM assumptions and also from Proposition 1. Okay, and lastly, Miller extends their 1958 paper. Okay, by now considering tax shields. So we're now taking the CAPM assumptions, but now we're relaxing the no tax assumption. So now we're allowed to have taxes, and we're going to assume that firms now can claim a tax rebate if they decide to lever up or take on leverage. Okay. So again, if you recall from lecture 1 or 2 weeks ago, this formula comes from the fact that I'm deducting interest payments from a firm's income, and then taking the tax, and then calculating the after-tax level. Okay, so let me show you what I did 1 or 2 weeks ago. So assuming CapEx, so I'm just going to assume that CapEx, capital expenditures, and depreciation, it doesn't exist, or they cancel each other out. So let's just assume that this is 0 and this is 0. And a firm every period just makes EBIT. Okay, so this is their cash flow. Okay, so if a country decides to rebate a firm for taking on leverage, then its total cash flow will be EBIT minus RD. So R is the interest payment, D is the debt level. So RD is the interest payments, total interest payments, and then times tau. And tau is our tax rate. Okay. So let's just, if we reduce this expression further, we will then get EBIT minus EBIT tau minus RD tau. Okay, and then we can group the EBIT expressions together to get EBIT times 1 minus tau minus RD tau. Okay, so this is each period cash flow. Okay, so if we believe that a firm exists into perpetuity, we simply just use the perpetuity formula and divide each of these components by its interest rate, right? So for EBIT tau, I would just use the WACC, and this will give me the all equity firm, right? All equity firm value, so that's V0, and R minus RD tau will be divided by R, and that will just give me minus DT. Okay, so minus DT is our tax shields. Sorry, this should be a plus. Yes, that would be our tax shields. Okay, so this expression here is the same as this expression here. So VD therefore is our levered firm. Okay, so I kind of already proved the proposition to you already. So we still exist in the world in which Modigliani-Miller holds, and we're still assuming that there's no bankruptcy costs. Okay, so proposition 3 basically states that the value of a levered firm equals to that of the unlevered firm plus that of the interest tax yield. So based on what I showed you here, the second bullet point is our conclusion, right? And so that's fairly simple. As I mentioned in the previous slide, everything is linear, so we can separate it, and we can just model each piece as if a separate perpetuity, and therefore our tax shield perpetuity is therefore just tau d. Okay, so proposition 1 still holds. If we include taxes, that's no problem, and therefore we can actually conclude that the firm value plus its tax shields value is still independent of its capital structure. Okay. debt over equity. Again, the upside down t means that they're not a function of each other. They're not dependent on one another. Okay, it just means that changing d over e won't change its overall value plus tax shields. Okay. So another way of saying this is that if debt over equity does impact firm value, it is only through its tax shields component. Okay. Okay. So let me summarize what I've shown you in this set of slides. So this is the last slide. Some of you might argue is that maybe there is heterogeneous preferences for certain types of securities. Maybe in this universe, there may be individuals that prefer equity over debt. Conversely, there may also be individuals that prefer debt over equity. And based on this supply of two separate types of individuals, a firm could potentially create value by issuing separate or two different types of securities, right? The question I pose here is that necessarily true within the Modigliani-Miller universe, right? Because Modigliani-Miller theorem actually sounds kind of counterintuitive. So based within the framework of what Modigliani-Miller presented, that is not true. Okay, so given frictionless markets and everybody can borrow the same interest rate, they buy and sell things at infinite amounts, no problem. What this is suggesting is that these individuals can also construct contracts among themselves and basically design any sort of contracts to satisfy their cash flow needs. So what they're saying is that investors' preferences are actually irrelevant within the Modigliani-Miller framework. The investors' preferences aren't over securities, it's actually over cash flows. Okay? And in the assumptions we made so far in this class, we're basically assuming that investors can trade at the same prices as firms, and there's no reason for investors to pay a premium for the firm to trade for them. Okay, so heterogeneous preferences or having a universe of different investors with different preferences is irrelevant, and it doesn't matter within our framework of corporate valuation. And so the firm should be focused on just matching preferences to cash flows and not matching security type to investor preferences, right? Okay, so that's what I hope everyone in this class takes away from this course. As you can see, this is quite deep in terms of intuition, and it becomes particularly relevant when you take advanced courses in corporate finance, when you deal in which a firm's capital structure does turn out to be relevant for valuation. This is particularly important for example, in Proposition 2 or 3. Okay, so under Proposition 3, it's basically actually stating almost like if a firm decides to take on leverage, they magically increase their firm value. Okay, in fact, if they can take on infinite leverage, they can just infinitely grow in value. So that's a bit problematic because that kind of contradicts reality. In reality, there are certain costs associated with taking on additional leverage, and that's because we have additional frictions in which stakeholders have competing interests. So imagine if you already leveraged and you already have existing creditors and you want to take on additional leverage. By doing so, you create conflict among existing creditors with future creditors. And that may prevent you from taking on additional leverage. Okay, so indeed, these costs will arise when you take on debt in reality, and we have to find ways to capture those costs. And that's something you will hopefully learn about in your future courses, especially when talking about buying firms using leverage and taking control of firms, especially when they have little or a lot of leverage. Okay, so hopefully this was enlightening, and this is something you can take with you into your future courses. All right, that's all I have for you today. So If you have any comments or questions, please leave them below. Otherwise, you can send me an email.